Today I will go on with the second part of the course, the mini course, and today I will try to discuss a little bit about how to validate solutions of linear differential equations with initial values, so IVPs, in the context of the validated rendezvous. So it's still in the context of space applications, but I will not insist so much today on the application, just a little bit in the beginning, and I will try to focus more on some tools that we use to validate differential equations. So just to have an example of ongoing example for our problem, I will define a little bit what the space rendezvous is. In its control, we try to design fuel optimal guidance law. In this case, the time is fixed, and we want to reach a given final position and velocity by consuming as few kerosene or few, depending on what we consider as the objective function to be. So we want to minimize this objective and still find a common law that allows us to reach the final position. So here, what I showed in the figure is an orbital rendezvous. So you have two objects, a target and a chaser, and they are in Earth orbit. Sorry, and in an Earth orbit. Well, so that's why we have an elliptical Earth orbit. So we have an eccentricity less than 1. And we consider that the chaser is equipped with impulsive thrusters. It means that it can move in very high bursts, but with very slow durations, and which can be, in principle, in practice, approximated as impulses or as Dirac functions. So in this case, we would like to find where the chaser should fire the engines in order to reach the target at the precise time with the precise given velocity and position. And this problem was studied in different dynamics. In this case, we consider that the objects are relatively close to each other, and so we can linearize their relative dynamics. And in this case, with this linearization, we can decompose the motion into the in-plane motion. So the chaser, of course, both the chaser and the target are moving around the Earth, so they have an elliptical orbit. And the chase with this linearization, we can decompose the movement of the chaser into a movement inside only in the orbit, what we call in plane, and a movement in the out of plane, which is in this case just a simple oscillator with this linearization. So then the movement is decoupled, and as you can see, this is a very simple oscillator, and the in-plane movement is a little bit more involved, depending on the true anomaly here that I told you. So once we have this uncontrolled dynamics, we add a control. So what I showed here is just an example of such a rendezvous. So the required position and velocity. So you know the initial vector state, the initial state vector. So you have position, velocity in plane, and also the final vector, state vector, and the duration of the rendezvous, and the eccentricity of the orbit, and so on. All the orbital parameters that you need. And we would like to minimize this this functional, this linear functional, on the control in order to minimize the consumption. So, and this is the dynamics that I showed before. Just replace the dynamics with the matrix A. Okay, and this is the control that we had. So it's a very nice problem, and to find the optimal control law here, and it has been studied already in the 60s by many researchers, and it can be proved that for this two-dimensional problem, so for the in-plane we have two positions, and out of plane one position, but they are decoupled. We have an optimal solution as two impulses in the out of plane and four impulses in the in-plane movement. So we have an a priori bound on the number of times that the thrusters should be fired in order to reach the final. So with this theoretical result, we can then design numerical algorithms, iterative numerical algorithms, that will allow us to find the exact times where the chaser should fire their engines in order to reach the target. But these are numerical convergent algorithms in real numbers, and we would like, of course, to validate afterwards that the numerical solution is good enough for the purposes that we have. So then the equation finally that we want to validate is something like this. So it's quite innocent looking, and of course we will validate it like this wise before the thrusters are fired, and then we change the initial positions, and then we restart the validation process, because we know that the solution is made out of impulses. So this is the, let's say, working example that I will use in the following in order to have some linear differential equation to validate. So as I said yesterday, when we want to validate some numerical computations, we have this kind of dichotomy strategy. So we go with validated computations with interval arithmetic or ball arithmetic and do all the computations, which is usually more costly and is more prone to dependency effect or to wrapping, so the rounding errors are accumulated. Or we can follow the second approach, in which we consider the numerical solution, and then we try to use a fixed point argument in order to prove that there is a unique, if possible, or at least that there is a fixed point not too far away from the numerical solution. Okay, so just to recall the most basic tool that we use to validate this kind of problem. So it's maybe the most current one is the Banach fixed point theorem, and what we require is to have a complete metric space X, and we have an operator, a map T, which we require to be contractive on a given ball. And in this case, by contraction, I mean that we can bound the Lipschitz constant of this operator, and this should be less than 1. And then if we can have an a priori estimate of how much the initial guess gets stranded by applying the map, then if we have a bound B on this distance, and if we can prove that the ball is strongly stable, meaning that this inequality is satisfied, then we know by Banach theorem that we will have a unique fixed point in the small green ball that you show here. So you have the big blue ball, and it's mapped inside the small green one, and then you have a fixed point. And of course, you can repeat this inclusion strategy in order to refine your. Okay, so based on this Banach principle, we can try to have different operators T to formulate, for instance, problems that require finding zeros of functions, for instance, as a fixed point problems. So here, if I have a solution of an operator, so I have a solution of an equation f x equals 0, then if f is differentiable, that I can build a Newton-like operator by considering the Jacobian, the inverse of the Jacobian of f at the initial guess, and of course this inverse, if I can compute it exactly, I have solved the problem because I just inverse the. But actually, it's more difficult to compute. So in principle, we are happy to have just some good approximation of the inverse, and then we consider so this new map, which becomes now a fixed point map, because we want to zeros of f implies zeros of this implies fixed points of this operator T. Okay, so with this construction, if now we can similarly, like in the we just apply again Banach fixed point theorem, but with this operator, Newton-like operator, then if we can have a bound on the Jacobian of T, then well, in this case, we only need a bound. If we can make it less than 1, then we can prove that it's contracting. And we have two cases. The easy case, when f is fine, when we deal with linear operators, then we can prove a global uniqueness. Otherwise, we will have only local uniqueness. If f is fine, then we can directly choose our air as this one, and we have proved the inclusion. Okay, otherwise, of course, I will only prove local existence or uniqueness, and I will have my mu depending on the radius of the initial ball that I chose. So to show how this works in a very, very simple case, I took an example from the PhD thesis of Florent. So thank you, Florent, for constructing this didactic example. So let's say that we want to find the root of this simple equation that so it's cosinus and sine, and we write it in like a simple polynomial system, and we want to apply the Newton-like operator that I showed before. So what I will do, so let's say we take we have one approximate guess for this root. Then we build the Newton-like operator that I showed before. So in this case, I can compute the inverse A approximately around at this root that approximate root that I chosen, and then I want to try to find a good B and a good R in order to prove the. So what I do, so I can choose different bounds, different balls around this initial guess, and check if this ball is strongly stable, meaning it will be mapped inside itself. So in this case, yes, it's not. Okay. Then I can change to make it smaller. So then in this case it is stable, and the constant mu is less than 1. And of course, I could take a very big one, in this case, yeah, it would be stable, but the constant would be very big. So then the only case that is valid for both requirements is this one among the choices that I made, and then I can prove that inside this ball that I've chosen a priori, there is a unique fixed point. So there is a unique root of my system. So this was the case for a finite dimensional system, and we can extend this Newton-like validation methods also for infinite dimensional systems by bounding very carefully the Q of the operator that we will construct, and we will try to do this in what form. So this was based on the fact that we are able to have a bound on the Lipschitz constant of the operator, or on the Jacobian, but maybe in some cases we don't have that. So if we don't, we can still use some very basic methods, and this was used maybe starting from the 60s, 70s, and it's also the basic tool for proving local existence and uniqueness of ODEs. So what we can do is just try with some sets and see if they by miracle they are mapped inside. And in this case, so for instance, it's just the fact that we can make it a little bit computable, constructive, that is interesting. Otherwise, just classical ODE theory. So in this case, if I have that my vector field is Lipschitz continuous with respect to the second variable, then I know that there is a unique solution in some neighborhood for some neighborhood of the initial condition for some time step, but I don't have explicit bounds on this. So I could just say, okay, maybe I can choose some step, and if ever I manage to prove this inclusion in interval arithmetic or some more fancy ball arithmetic, then I can say that at least on this interval 0h, I have a unique solution for each initial condition in the set that I consider. But of course, since if ever my vector field has a big Lipschitz constant, I will have to take a time step very small to compensate for this. But it's a brutal method that sometimes works well, and or provides just some a priori rough enclosure to start somewhere. After that, to improve on that. So I also gave, just for pure, if you are interested, the proof is quite nice in the sense that you just apply again Banach point theorem, because you know that with respect to a nice norm, your operator is your fixed point operator that is obtained by building the integral version of the initial ODE is a contractant, and then you apply again Banach fixed point theorem. So of course we could try to build a computer bound for this Lipschitz constant, but we do not need it. If we have it, we can use this as an a priori bound also. But if we do not, if ever we just manage to prove the enclosure, we are lucky, and we can build from there. Okay, this is like the very basic method that people use with interval arithmetic to be able to prove something. And of course, since then, there have been a lot of methods that were developed, and I tried to do some chronological, but of course not exhaustive, list of some works that I find interesting. So, as I said, the first works based on interval arithmetic were already in the 60s, and Moore already has a paper on how to do this contraction mapping with intervals. Then a lot of people build from that, and of course, instead of using just one interval, if the vector field is smooth, we can try to have a Taylor series and use a ball arithmetic with some power series if we want. And so these were more on like this, like building different ways, the Taylor series, and mostly using this kind of Taylor models, which is an kind of an algebra of a Taylor series. And but then there were like pure computer algebra methods that were developed, for instance, by Joris or Mark, and they were also based on Majorana series for the finite functions, but can be extended for various ODEs. And I also listed some software that can be used for doing this enclosure, this iteration of OD. So on these were more on Taylor series. Then already in '82 there was a paper by Coucher and Miracle, who said that okay, we do not have always to use Taylor series. Why not use all generalized Fourier series? They have in '82, and already they say okay, we could be replace floating point with just a series plus error bounds, and we should be already computing this algebra. So it's quite nice to read, because these problems are still very much studied today. So and of course they have exactly the same motivation, that the floating point is has a rounding error. So maybe we should bound everything, have an arithmetic of sets, and so on. And there were some other works in the meantime, and then this approach was revived in not in the last 10 years by researchers in computer algebra here present, and also there is also some works more from the dynamical systems community, where people, especially Jean-Philippe Lessard, already in '98, Yamamoto used different expansions, orthogonal expansions, the Chebyshev series or other Fourier series for function of the ODE they were handling to prove enclosure of the solution. So my motivation to use Chebyshev series instead of power series came from the need of doing repeated evaluations, for instance, in moderate precision for interpolation, for integration, for plotting. The idea is that with respect to power series, Chebyshev series have a better convergence with respect to the infinite norm and to the supremum norm. If you want, they are also what we call near best approximations with respect to the uniform norm. And so having a machinery that is automated with respect to Chebyshev series could be as a proof of concept for other orthogonal polynomials that would correspond to, say, different domains for different ODEs appearing in practice. So as I was mentioning just on the previous slide, so the Taylor series that I show here, that everybody knows. So analogously, the Chebyshev series are built with respect to the orthogonal polynomials Tn, which are orthogonal with respect to this measure. And well, they are just polynomials that have the interesting property of having exactly n roots in between -1 and 1, and also they equioscillate between -1 and 1. And if we take, for instance, two approximations of fixed degree with respect to Taylor series or with respect to Chebyshev series, we observe that the Mach norm, the uniform norm, is better for Chebyshev. So if we want some moderate precision approximation, very smooth on some bigger interval, will be scaled down to -1, 1, then sometimes it's better to use Chebyshev. And also the reason, another reason is if your function has singularities in the complex plane near the real line, then what we know that Chebyshev series will always converge on an ellipse with the foci in -1, 1. So if you are just interested in having a convergent approximation on -1, 1, but you have like very, very close singularity to the real line, and you can still use Chebyshev. Otherwise, you will have to cut your domain and use a smaller disk and analytic approximation if you want to pass over your singularity or something like that. So, of course, there is a trade-off to be made, whether it's better to use more disks or just one ellipsoid, depending on the application that you have. And as I was saying, this Chebyshev truncated series, they are also very good uniform norm approximates in the sense that they are very, very similar to the best polynomial approximation in a uniform norm, which is also called the Minimax polynomial. And we see here that if we do not want to spend a lot of computation to actually compute the best polynomial approximation of fixed degree, we can sometimes also do it just a truncated Chebyshev series, because the difference between the two will be very small. And yeah, well, in terms of supremum norm, we lose very little if we are interested, for instance, in the implementation of some of our favorite elementary function or in fixed precision. Okay, so now that we know a little bit about the Chebyshev series, let's see how we can build validated approximations in Chebyshev series for linear ODEs. So just to fix a little bit the mathematical background, of course, if we take a linear differential operator, which is not singular in this case, we know by Cauchy-Lipschitz theorem that we will have a basis of solutions in the order of the differential equation, and we will have for each initial condition a unique solution. So from a mathematical perspective, there is nothing left to be done, let's say. It's not like we will prove some Navier-Stokes or something, okay? It's just this is like a basic brick for what we want to use afterwards. But we still are interested in having software that can have very efficient Chebyshev series approximation for this kind of problem. So what we can do? So as I said, well, we consider our linear differential operator, and first we try to build some numerical approximation. And today I want to show two methods. Of course, there are also a plethora of methods, of spectral methods, in order to build Chebyshev approximations for linear ODEs. But my favorite two, and since I give the course, you have to support me, are, one coming mainly from the computer algebra community, and it's based, of course, on recurrences that the coefficient of Chebyshev series satisfy, similar to what I showed yesterday for power series. And then I will also talk about a purely numerical one that's very efficient, that is a spectral projection method. And then once we have our favorite numerical approximation built with our favorite method, then we try to apply the machinery of doing this Newton operator-based validation. So this is the plan for what follows. So let's start with the computer algebra approach. So a nice property that Chebyshev series also share with power series, former power series that I already talked about yesterday, is that as for power series, if Chebyshev series is solution to a linear differential equation with polynomial coefficients, that is a finite operator, then also its sequence of coefficients is also cancelled by a linear recurrence with polynomial coefficients, like I showed yesterday for power series. So this there is a sequence of articles in literature, and I became aware of this problem when I saw a talk of Alexandre Benoit in 2009, exactly here at GNC. So, but the history of this problem is as you see, goes already in the 70s. Some primary results on this problem were already available. So, in contrast to power series, where we have the initial conditions to start our recurrence, for Chebyshev series, the story is a little bit more complicated. Quite a bit more complicated, in the sense that even if we try to unroll the recurrence in a straightforward manner, like we would say for Taylor, for instance, I have my recurrence. I just unroll it. So here is the numerical results, and here is the expected good results that I expect to have. So here we observe that there is no loss of precision in this case. But if I do the same for Chebyshev series, suppose somebody gives me the initial conditions. Of course, they will not be exact, but they have a lot of correct digits, and I just want to unroll the recurrence. Well, in this case, I have completely lost my precision, and this will happen generically, even if I try to put like more digits here. Then when I will unroll up to higher order, everything will be. So here I is the Bessel I function, which is the initial condition for the exponential in a Chebyshev series. So the intuitive reason why this happens is that my recurrence for the Chebyshev expansion has actually two independent solutions depending on the initial condition that I put, and one will be, yes? Oh, okay, so I thought that, yeah, okay. So one will be convergent and one will be divergent, and then if I try to unroll the convergent one, which I will, because my series is convergent, I will get attracted to the divergent one, and it suffices to put a little error. Then I will actually go towards the divergent part as manifold, and then I cannot apply this method like directly. Okay, so this is the.
Sorry. Can you tell us what is the relation between in of 1 and un in the recurrence relation that you write below?
So in of 1 is exactly what should be the un of actually, okay. So in of 1 is un. Okay. So what you want to compute here? So is in of 1, but in fact what you compute is kn of 1, basically, with a constant, let's say, multiply with the constant. So in principle, you follow the asymptotic of the wrong one. Okay, because it exists. Because for the same recurrence, you have if you put k 0 of 1, you will get this one, and if you put I 0 of 1, you will get this one. But since this one is divergent, as soon as you want as soon as your condition is a linear combination of a little bit of kn of 1, you will end up obtaining the values of kn of 1, more or less.
What you're saying? This phenomenon of divergent solution may appear. This phenomenon of divergent solution may appear on the Taylor expansion side, right?
Yeah, but
what you say is that when you do the conversion, it will systematically happen on the Chebyshev side. Right?
Yes.
Okay.
So on the Chebyshev side, we will actually have a recurrence of 2n of order 2. So I will have n convergent solutions and n divergent, and we can prove actually that we can prove some nice properties about the recurrence, which, for instance, state that for a given Chebyshev recurrence, if I know it comes from a Chebyshev series, then I will have my real, my true power series, my two coefficient series will be on from the convergent ones, and I will have, and it also will be symmetrical if I take all the solutions. So from minus infinity.
Okay.
Yes, so I will have a lot of properties that will help choose from the basis of solutions which one is the good one. So in this case, for instance, a solution to be able to solve this problem, at least numerically, is to say, okay, if anyhow, when I unroll forward my recurrence, I will go to this divergent one. But if I start from some very high coefficient and a high index coefficient, and I try to unroll my recurrence backward, then, well, the phenomenon will be just reversed, because now this one will become the convergent one, and this one the divergent. So this is exactly the trick that was already used in an algorithm called by Miller. And in the basic case, this is how we proceed. What we do is, okay, we try to unroll so backward the recurrence, but I put some well, I don't know what the U of 52 will be exactly, so I can just put some standard initial conditions. Then I unroll my recurrence backward, and then I have an initial condition more or less because I have f of 0, and I can compute this constant with these conditions, and then by dividing this, so because I have the actual initial condition, in this case is 1, I can just divide by this constant and obtain accurate, and we don't know how much accurate, values of the coefficient, true coefficient of my right. So of course this is just an intuitive view of how we should unroll backwards the recurrences, but this generalizes to recurrences of a higher order, and there is well, we work with Marc and Alexandre Benoit at the time on building an algorithm that that is able to compute good approximations of these coefficients by unrolling backward the in the same. But there are some complicated technical proofs in order to prove that it actually works when we have singularities, tail and head singularities in the recurrence. And I do not want to enter this because, well, it's a little bit overkill, but just the numerical method is quite, if we do not have to prove the actual accuracy of that we obtain. So let's say we can use this Chebyshev series, numerical Chebyshev series, or otherwise we could try to use a different numerical algorithm. The advantage of the algorithm that I proposed before is that it runs in linear time, because I only have to linear plus something if I have singularities in the tail and head of the recurrence, but still in linear time if I have to compute numerically my recurrence. But there are other algorithms that come more from the numerical community that make use of sparse and of structured matrices in order to obtain a similar complexity. So this is one that I want to talk about. And to do so, I will have to convert my differential equation to the integral one. We can do it also directly from the differential equation, but it's not so nice. So I will do it from the integral one. Okay, so to take my initial example, where I fixed now the eccentricity to 0.5, and I fixed some initial conditions, I can fix the second derivative to be phi, and I can build an integral operator on phi. So I just integrate twice my my differential equation, and I have this integral operator. And in order to fix to have my Newton-like method work, I will have to place this operator to act on some functions. And in this case, I will fix a Banach space with respect to this norm. So this is an upper bound for the infinity norm, which is the sum of the absolute value of the Chebyshev coefficients. And with respect to this norm, we have a Banach space that is that contains all the functions that are continuous and are convergent with respect to this norm. And we also can prove that this becomes a Banach algebra. It will be nicer to prove bounds than on the coefficient. And yeah, so this is the Banach space Ch, and this is Florent who coined the letter. And I said, okay, it's a nice letter for today, no provocation. And so this Banach space Q that I will use in the following is just to be able to have a background for applying my Newton-like operator. And from this one, how can, of course, it's an infinite dimensional operator. How can I obtain an efficient solution? So it would be nice to be able to truncate somehow and solve a linear system. So this is what most numerical methods use. So they will project something and try to have a finite dimensional linear equation to solve. So in our case, we will try to do the same. So firstly, let's first approximate our coefficients with some Taylor series. So let's put for this one coefficient some this just for the like a polynomial of degree 2, just for the sake of the example, and then my operator becomes something like this, and now I can see how this operator acts on a Chebyshev series that I test Chebyshev series, and for that I will start with all the polynomials in the basis. So let's see how it acts on the on one polynomial. So we see that my ith Chebyshev polynomial will be sent on the will be set on the so if you look at the operator as a matrix, then you see when you apply your operator on a basis how the matrix will get filled up, and we see how the indexes, what indexes are filled in here. So actually, if you multiply two Chebyshev polynomials, you will impact the I minus j and I plus j new coefficients of the new series. It's not like it's a bit more complicated than the Taylor series, where you know that it will impact only on the I plus j coefficient. Here you have two of them, and then when you have integration, you will impact. So integration will impact on 0 on the 0 I plus j minus 1 and I minus j minus 1. So it's analogous to Taylor, but you will based on what it means to multiply two Chebyshev polynomials and or to integrate one. And we can also see how the coefficients will decrease. So for instance, with integration, we see that these coefficients will decrease in 1 over I. And if we put this trick of starting our integration for -1, then we can prove that the constant coefficient will decrease in 1 over I squared. This would be nicer to have a tighter bound. Okay, and then when also I multiply with a polynomial bj, then I will, of course, this is just the same, the analogous of the same operator. Okay, so and I can also bound the coefficients obtained by integrating this and multiplying by polynomial of bj by this. So it's nice. I have once I apply my integrator map, I can have bounds on the tail of the series. Okay, and so what we see here is that actually only few coefficients will appear in the matrix representation of my operator, and I can bound which is the maximum degree for each ti where it will where the matrix will get filled, and I can prove that actually the operator will have an almost bounded matrix. And here is a drawing. So because, as I said, so you get all the constant coefficients, so few constant coefficients here, and then you have a banded operator, because you always have I plus j, I minus j, and then you have around the diagonal I plus j, I minus j. Okay, and then this is what is called often called an almost banded operator, because you also have this band, horizontal band here, and we can prove that this operator is compact, meaning that when you go to infinity, these coefficients will vanish rapidly, and so it's only natural to truncate it and to solve the corresponding linear system. And this linear system can be very efficient to solve by a method of Olver and Townsend, which uses a nice QR decomposition of this almost banded operator. So we are not forced to have the standard complexity of a dense operator. Okay. So if we do this, we solve the truncated system. We will, as I said, we will truncate our operator, and we have the matrix representation. I just solve it. I take a right-hand side of degree 3, and I apply Olver-Townsend algorithm, and I have this solution, numerical solution for a truncation. And what I say here is that okay, I truncate my matrix that you have here. It will become an n by n. This is the truncation that I Okay, so now we have our favorite numerical method to obtain in, let's say, linear time an accurate approximation in Chebyshev series. And we could either use recurrences, or we could use this truncation operator and solve the linear series. Okay, so now the only thing left is to validate the thing. If we want, we could also say, okay, and numerically sufficient, and we stop here. We have a good complexity. But the whole point of this course was to also do validation. So let's see how we can finish it. So it's quite similar to what we did in the truncation part, but we have to handle the infinite dimensional part that we just ignored before. So in this case, so I will have this exact equation to solve, but I will only be able to have access to a truncated operator or truncated inverse of my operator. And as I showed before, we can, in a similar way, build a Newton-like method here. So instead of, we cannot invert 1 plus k completely because it's infinite dimensional, but I can have k truncated at order n. So maybe I can invert I plus kn numerically, and this will give me some a here. And it doesn't have to be the exact inverse of the truncation, just have to be a sufficiently good one. And then I can try to apply the Newton-like method, and if I can apply Banach fixed-point theorem, I have proven mine. So for that, of course, I have, like in the finite dimensional case, I will have to bound the norm of this operator. In this case, it really has to be a norm on the infinite dimensional operator. So I have to build a nice procedure, a nice algorithm, in order to be able to bound all the Q coefficients in my operator and have some bound k that is less than 1 in order to prove that this operator is contractible. Okay, so if I can do that, then I use Banach, and I have 2 bounds for the numerical equation. So how to obtain first the numerical inverse? What complexity can we achieve to get the numerical inverse? So we choose a truncation order n. If we compute directly the inverse, then it will be a dense inverse, and we have a quadratic complexity in the truncation order. But in some cases, it turns out that we can also approximate this as by not computing the exact inverse, because we see that the coefficients here are very small. So we could ignore them and use just some few terms of the Neumann series, and then I will have an approximation, maybe sufficiently good, of the exact person, and with it will be also almost bending, which is nice because we keep the complexity linear with n. But yeah, it sometimes may not be sufficiently. So it's not in all the cases that we can have an almost banded operator for the int. But in practice, in some cases, we were able to. And so once we have this A computed, then we will split the error that we have to bound into parts. So one will be simpler in the sense that it will only measure the fact that A is not the exact inverse of I plus n. So this will be what I will call approximation error. And this will be finite dimensional because I plus k n and A are finite dimensional. So this is nice to bound. It's nicer to bound. We can just use some like at least the interval arithmetic or some better bounds, cleverer bounds, but this is easier to do. And the more difficult part is this one, which is the truncation error, where actually I'm considering the Q of my infinite dimensional operator that I have to multiply with the approximative one. So for this one, that I consider first, we can in principle use arithmetic on almost banded matrices and have a good complexity. And for my example, this is what we get to wrap up. On the other hand, for the infinite dimensional part, I have to work a little bit more. So to see what happens, so this is my initial operator. I cut the nth truncation of this, and then I multiply by A extended by identity on the infinite part. So now I have to bound all these parts. So I will, by multiplying, I will have several regions. So for instance, here I will have just few coefficients that I can compute and bound directly. Then okay, so they are here. Then I will have this part that is still finite dimensional, and I still can bound easily. And then I will have the real Q of my operator, where I have to use some a priori bound. And as I showed before, for this case, we prove that they are in 1 over I squared. So I will use this bound on them. Okay, and so if we do this for our example, so for the first part we have this bound, then this bound, this one. For this one on top is on 1 over I squared, and this is on 1 over I. And then if we add everything, then I get a bound on the truncation error, and I had the approximation error before. So then I get a bound on my k constant of my operator that I wanted to have less than 1, and in this case it works. So we have proven that our operator is contraction, and now we can just compute our B. So this was called B in the finite dimensional case, and it measures the defect of applying the operator, and we get a bound very small, because in this case I took anyhow a good numerical solution. So in total, then I can bound the total error between the numerical and the exact, the fixed point of my operator. It will be, in this case, work like. Okay, so this is the the whole procedure in principle for linear differential equations. So we use this integral reformulation. Then we use our favorite numerical method, and then we create this kind of almost bounded operator and bound the different truncations and approximations error that we. Okay, so if in the case that this will always be almost bounded, and if this is also almost bounded, we stay in linear time with respect to the truncation order. Otherwise, we will have here n square if this is not almost. So for the examples that I showed with the rendezvous problem, so for now a more realistic example. So this is for a real rendezvous. So it was a supply mission for the SS, I guess. And okay, so if these are the impulsions where we have to fire our engines, this is the numerical solution that we obtain in the orbital plane, xz plane. And if we apply this machinery, we want to certify that we land in the end where we want. So this is the bounds that we obtain for different degrees of Chebyshev series. So if this you see here the accuracy is not very good, then while we increase the degree, we obtain for closer and closer enclosures we want. This is some numerical results to have an idea of how it works. Right. And if we take a more complicated example, like here we have a long ATV mission, and you see here that it's a quite oscillatory trajectory, and still we can get good bounds, but we have to go to high degrees in the Chebyshev series. To get one approximation on the whole time. Otherwise, of course, if you cut, you can do Taylor or you can do Chebyshev on higher, bigger chunks. But if we want to have a uniform approximation between the two firing places, these are the degrees that we have to. Okay, so actually, yes.
In terms of the degree,
with respect to the regularity of
yes, some regularity of the function.
Yes, yes. So you have exactly the same bound as for Taylor, but you can divide it by 2 to the n. So it's 2 to the n better than what you could have
so
for.
What is it? It's 1 over n.
So you can bound it by like for Taylor with Cauchy, for instance. So by m over n factorial times z to the n. So like the n, like the term on the Taylor series. And for Chebyshev, you will have also so n factorial times over 2 to the n. So it's 2 to the n better than the bound that you will get for Taylor series for analytic functions. And if you consider functions that are not analytic, then you will get convergence rates that will be, I think, for for Lipschitz continuous functions, it will be the worst convergence rate. It will be just 1 over n. Yeah, you have bound. Yeah.
And the constant. You have an estimation of the constant also?
Yes, I think you can have something like I showed for the Lipschitz constant. I think you can have the same.
Thank you.
Yeah, so we know for the Chebyshev series we can have this a priori. Mark, you can ask because it's you can ask if you want to ask a question. Yeah, you feel that the degree is too big, or okay, good. So are there any questions? So I think I have also regarding the convergence. I think I have a slide somewhere. Just wait to see. Maybe I put. Yeah. So as soon. Yeah. So we will have, as I said, I think we will have for Lipschitz continuous. We will have better convergence rates. Do I have something? Yeah. So as soon as you are. So yeah, this is. If you are C1, then you are in 1 over n, as I said. And then if you are better, so you will have algebraic. And then if you are analytic, then you will have similar convergence like for Taylor, but you will have a better, will have a, yeah, it's a term. The O, I think you have, you can, for, I think for instance, for analytic functions, you can, for instance, bound it by the end plus 1 psi. So you have something like the analogous of Lagrange remainder for Taylor. So it's something like n times n plus 1. Okay, and then you can also try to bound this. So this will be your f. Okay, so as I said, but nobody figured because you're all sleeping. I cheated. I cheated a little bit on the complexity estimate. And why is that? So, yeah, everything I said was correct, but so I computed my complexity estimate with respect to the truncation order of my operator. But I did not compute it with respect to the actual degree of the approximation that I want to certify. Okay, so with respect to this truncation n, as I showed the approximation and truncation error, with respect to this norm, we can prove that indeed we have a bound of this form. So if both A and K are almost bounded, then here we only have n. Otherwise, in worst case scenario, we have n squared. And R plus S are just the bounds on the bound on my almost bounded operator. R is also identified with the degree of my the order of my differential operator, and S with the degree of the biggest polynomial that I have in my differential operator. So I have this number of arithmetic operations, and this is my n, the degree of the polynomial that I actually want, of the truncation of the series that I actually want to validate. And thing is that this n can become exponential with respect to the norm of the coefficients of my differential operator. So then with respect to n, I will have a very bad bound in some cases when for instance, when my differential equation is what I call stiff. Okay, so the thing is that when I truncate this operator, in a way, I bound the Lipschitz constants for all the bases of solutions that can that my differential equation can have. And I can only have a decrease, as I showed, in 1 over I when I integrate my, and I cannot really harness the fact that these coefficients, in fact, may decrease faster for some solution and for others. So this is an issue, and of course, after Florent finished his thesis, he became smarter, way smarter, and he now he was able to use a little different trick and to truncate actually the resolvent kernel of the integral operator, and not the one that I showed. And in this case, he can have a little better bound. In practice, it turns out to be quite a nice speed up and a nice increase in the speed up, in the sense that for the same degree, you are able to validate a better bound, and then you can use a lower degree polynomial. So, and in this case, he proved that we can only have a complexity on n, which depends polynomially on the norm of A. Okay, so this kind of concludes the main ideas that I wanted to share with you. And I just want to finish with maybe some future works, some general trends in this field. So yeah, the main quest kind of remains similar to the people in the 60s, in the 80s. So we really want to get to solve problems with the desired accuracy, and numerical methods, most of them do not provide that currently. So for this reason, we try to use various symbolic numeric algorithms. I showed just a little fraction of them. For further, if you want to read further and to explore like newer interesting algorithms on partial differential equations, for instance, there is this nice book of Nakao, Plum, and Watanabe that it's quite recent, and yeah, here you can find still the same flavor of Newton-like operators, but applied in different functional spaces. So there is a core idea of building this fixed point operator in a suitable functional space that stays, but they use different series. They use Fourier series, they use splines. So depending on the problem and on the domain of your ODE, you can use different truncated series. Okay, so these are more like there is not so much complexity involved, so it's more like people show how it works, but there are no really generic complexity results on what's the best complexity arithmetic or bit complexity that we can achieve for solving certain classes, generic classes of ODEs or something like that. So this is also a thing that would be nice to have. And of course, there is a trade-off to be made, whether we also want to prepare our proofs for formal proving. In this case, turns out that this Newton-like method is often nice because you can just use your numerical favorite tool to get a good approximation and then just prove this inclusion. Okay, so this is kind of the trends that I identify. Thank you again for your attention.
Thank you, Mioara. Are there any questions?
in the past there was work to obtain recurrences for coefficients along other, for series using something else than Chebyshev. So,
Yes.
so are there other orthogonal polynomial families that would be of interest to you?
Yes, of course. Yes. So the work of Alexandre and Bruno, Alexandre Benoit and Bruno Salvi, to be able to construct recurrences, annihilating operators for the recurrences based on the differential operators for other orthogonal polynomials. It would be nice if we could apply it also on the to study the numerical properties of the recurrence obtained and be able to use it numerically first, and then of course for instance, let's say for all that's periodic ODEs, people want to use Fourier, obvious, but then there are other domains on which we can use different families. I saw quite bizarre families that can be used for instance, not even like really generalized Fourier series. I saw a talk using series in Bessel functions. So yeah, so this kind of we have quite different orthogonal polynomials we could use. There is also, for instance, if we want to propagate Gaussian distributions, then we would be interested in having some polynomials that are orthogonal with respect with the Gaussian measures or something like that. So there are a lot of people who use this kind of orthogonal, I mean L2 series with respect to different different weights. So for instance, for Gaussian, it's Hermite, and so on. So for me, maybe Hermite would be the nicest to try something with at the moment.
Maybe you can use the second kind, Chebyshev polynomials, which are also orthogonal polynomials and which are the derivative of the
yes. So,
kind.
but this will be also good with respect, I think, still with respect to the infinite norm. I think they will, because if you do the collocation for both, you can use either if you pass on the discrete quadrature, you have that instead of using the Chebyshev polynomials of first kind, which correspond to the roots of the Pn, then you can also use the roots of Un, which is the second. So this will also give near best. So I think Un may be also good still for problems that are on bounded intervals. But then it depends on your domain. If your domain is the straight line, it may be, and you are periodic, maybe you want Fourier. If you have like an unbounded domain of initial conditions, but which follow distribution like Gaussian, then maybe you want Hermite, and so on. So it depends on, with respect to what your family of what norm. Let's say if you want some specific norm, your family of orthogonal polynomial is, or.
Okay.
But I think UN will be, because I think UN will give exactly the same, like a similar bounded operators, and so UN will be similar to this one. Yeah.
Any other questions from Mioara?
Excuse me. I have actually two questions, maybe a little bit technical, but I didn't manage to understand if the matrices I plus k you consider here is indeed invertible, or if or not.
Yeah, we can prove that that our operator is invertible. Yeah.
Okay.
Yeah.
Okay.
Yeah, we know that it's injective, and we can prove that it also surjective. Using the Fred-Dorman alternative, and then we can prove that
the truncation you consider are also invertible?
I guess so.
Okay.
Yeah.
Thank you.
But maybe we can. I mean, otherwise you can just increase the. I don't know if we can prove that for each. For each, I don't know if you can prove that for each n it's invertible. But I mean, it's you know that it's invertible on.
And my second question is that the problem you want to solve at first for this rendezvous problem, there is a differential equation with some cosine in there as a denominator, and it seems to me that at some point you replace them by polynomials of degree 2,
yes.
and in order to get some your band matrix, and at the end you forgot about this problem.
I'm glad that somebody identified the second cheating in this talk. So indeed, so this what I showed is the algorithm for definite functions, and if the coefficients that I have are sufficiently regular, then I can also bound the remaining part, which just the remainders, the errors. But I don't have if they are not sufficiently smooth, then you cannot approximate them by Chebyshev series. But if you can, then you just do the. I didn't do it here, but you can bound also the small remainders that. And for this you can use an algebra with Taylor series directly or something.
Thank you.
Thank you.
Any other questions? No. Well, maybe we can thank Mioara again.